Hi, everyone. I'm hoping that my screen will pop up and that you're seeing it nice and clearly. Thank you, Lisa, for a really nice introduction. And I want to thank all of you actually for joining along in and providing me the opportunity to be able to share this information with you. And in an ideal world, I was actually very much looking forward to seeing the library and meeting many of you in person, but we'll make the best of what, as Lisa said, the modern technology will provide. So I hope while I've been chatting here that you've had a chance to look at background. This is an artist's rendition of the Arctic 100 million years ago. And it's been drawn on the basis of varying kinds of geologic data. You can see the odd shimmer in the background. That's the aurora borealis, or the polar northern lights. The creature perched on the side of the water is a crocodile-like reptile. And the trees that are surrounding the water are your typical forest trees of the temperate zone. But remember, this is the Arctic. So back 100 million years ago, this world was much warmer than it is today, on the par about 2 times that of today. And the volcano in the background on the left shows you all these gases that are being spewed out, greenhouse gases, water vapor, carbon dioxide, methane. And this is the source of this warming at this time. We call this, these kinds of reconstructions deep time, or time slices in the earth well before humans roamed the earth, and in many cases very different than today. And you might say, well, okay, this is intriguing, but how relevant is this to our future? And that leads me to my main message tonight, which is that I'd like to share with you. And that is that the deep time geologic record makes a unique contribution to climate change discussions. More specifically, this geologic record is our only repository into insight into how the Earth's system will function in the evolving CO2 environment that we anticipate in our future. So let's start with today's CO2 concentration in the atmosphere, and which, by the way, it's 414 parts per million. This is a level comparable to about 3 million years ago. And this plot shows the measurements of atmospheric CO2 over the last 60 years. These are measured in real time over the Mauna Loa crater on the Big Island of Hawaii. And the current values of 414 parts per million are 35% higher than any time in the last 800,000 years. These CO2 concentrations have been rising at 2 parts per million per year since we turned over into this millennium. So at this current rate of rise, we will be looking at CO2 in the atmosphere by the end of this century, potentially at a level that we haven't seen for tens of millions of years. Now, I think we all appreciate the source of this exponential rise in CO2 in the atmosphere. And the plot you're seeing here are CO2 emissions due to human-based activities, what we call anthropogenic CO2. So the rise in those emissions since the beginning of our industrial era, about the late 1800s, when we started to burn coal, oil, gas for energy and transportation and things like that. You can see the exponential rise. We hit a peak, we thought, somewhere around the turn of the millennium, when values were at their fastest increase per year. And then in around 2014, it looked like the growth rate of CO2 emissions to the atmosphere slowed down. And in 2017 and again in 2018, we hit actually a new peak, suggesting that we are not yet at whatever may be the peak in release of anthropogenic CO2 to the atmosphere. So the importance of not having reached this peak in CO2 to the atmosphere is shown in this graph. And what you're looking at here on the vertical axis is the net CO2 emissions, or total emissions to the atmosphere over the time period of 1980 to 2100. So the black line is what we have put into the atmosphere to date. And the colored lines and the gray curves are those projected for the future in this century based on different CO2 emission scenarios, meaning deciding on based on how we might change our use of fossil fuels around the world. And I think what you can see is that no matter what scenario we are on for the future, we are kind of hard pressed to have temperatures. I'm sorry, this is very sensitive here. Let me go back. We are hard pressed to remain at temperatures shown here on the right below 2 degrees Celsius. And the importance of that remaining below that 2 degrees Celsius is that that is the threshold that we best appreciate now based on scientific evidence. That is a threshold after which we will start to see catastrophic changes related to warming. Now, this issue of reaching a new high in 2017 and 18 largely reflects a 3.5 increase in carbon emissions in China in those 2 years. And what that was related to was a long-term drought over a broad swath of China. And that country, which still uses a lot of coal for its electricity, has been moving towards hydropower as well. But with that drought, which they believe was climate change driven, that meant there was less water available for hydropower use. And that meant they switched over to more coal burning. And more coal burning then would have a positive or reinforcing effect, what we call feedback, on climate. And these positive feedbacks or reinforcing feedbacks is something that we can anticipate with greater frequency in the future as conditions get warmer. So I'd like to look at our CO2 in the atmosphere today and into our future in the context of our past. And what you're looking at here, actually, let me tell you first that we have various ways to actually reconstruct CO2 in the past. And for the more recent past, the last million years or so, we actually can use ice cores. And what you see here is an ice core from Greenland. And the CO2 is actually trapped in bubbles in this ice core. And what you're looking at the bottom then is the record over 400,000 years on the horizontal axis here. So in blue, the CO2 concentrations over that 400,000 year period. I have to hesitate using my mouse here to show you things. The CO2 over the 400,000 years and how it has systematically varied. When CO2 was at its higher point at about 300 parts per million, the ice that was present over North America and Europe retracted well back into Canada and into Russia. But when CO2 was low, down at around 200 parts per million, for each of these 4 cycles, the ice waxed well into the United States and well into much of Northern Europe. But you can see that generally CO2 was staying between 200 and 300 parts per million, very systematically fluctuating. This break in the trend, this exponential increase here at the end, is the anthropogenic CO2 of the last 100 years. So there we are, 414 parts per million, that red star. And projecting into the future is always a bit more challenging, but I think the estimates are converging on a value of about 650 parts per million, plus maybe 100 in either direction. And if we continue on the business as usual path, meaning the rate of fossil fuel burning and CO2 emissions to the atmosphere that we are on currently, we could be looking at a value of about 1,000 parts per million, sometime at the end of this century or beginning into the next. And I'd like you to keep that number of 1,000 parts per million in mind, because that's going to come up later in this talk, and I think it'll be interesting to make the comparison. So with this diagram, I'm going to be asking how far back in the past or in the geologic record do we have to dial back the clock to time where the conditions were equivalent to what we might anticipate in our future. Now, this is a busy diagram, so I'm going to take some time to walk you through it. On the top are 4 globes, and these globes are showing you the temperatures in shades of pale to darker orange for past periods of global warming, as far back as 90 million years. And below them is the average surface temperature at that time. The blue globe on the right is that for the last time we had these waxing ice sheets, 20,000 years ago, that came well into New York, Minnesota, Illinois, Montana, Oregon, Washington. Excuse me. The temperature then was 14 degrees on average around the globe, and today it is 15 degrees on average. When you look at the center of the graph, the gray line, that is the best estimate we have for CO2 for the last 100 million years. And I think you can see that for the last 34 million years, that CO2 has been decreasing pretty progressively to where we were recently. And above there, in the orange to yellow trend, are the surface temperatures over the same time period. And you can see during that 34 million years of fall in CO2 that the temperatures halved on Earth. To the right, these very steeply rising gray curves are the projections for CO2 in the atmosphere for the next 200 years. And beside them to the right are globes showing the increased temperatures that we might see associated with these increasing CO2. The top one being the business as usual scenario for 200 years from now. And I think you can see clearly that that 2 degree of warming, that threshold under which we want to remain, is only valid for the most conservative CO2 emissions released to the atmosphere, and would require that we peak in our emissions in the next 12 years or so. So if you look at the business as usual emissions, and even the intermediate scenario, we could be looking at CO2 levels sometime in the next 200 years that we haven't seen for 34 million years. And that's what the arrow is pointing out. And if you take your eyes and go right directly upward of that, you'll see that that is at the time right when we start to have ice on Earth. So conditions that really aren't stable for ice sheets at our poles. So taking this whole diagram together, I think one can say that clearly the paleoclimates or climates of the past are our future. So what you're looking at here then is changes in temperature for the last 130 years, or since we started burning fossil fuels. And this is for 4 different agencies that have been tracking this increase in temperature. And what you're actually seeing is a temperature anomaly relative to that interval that is shaded in gray, the interval between 1950 and 1980. And they've chosen that because you can see that the temperatures before that are generally below that average. And certainly the 3 decades after that, or the most recent 3 decades, show that very rapid rise in our Earth's surface temperatures. In fact, those are 3 decades of temperatures hotter than any time in our last 1,400 years. Sorry. This is extremely sensitive mouse tonight. I don't know why. I think it's the way that this, let's see, okay. And I don't know, excuse me, I apologize. Okay, so this is a timeline I'm gonna show you a couple of times. It is in millions of years, or 100, 200, and so on, millions of years. And all I'm trying to illustrate with this very simple timeline is by the blue and yellow colors, the 2 major climate states that have existed in Earth's history. In blue are what we call ice house times, times where we have ice sheets at least covering one of our poles. Today, of course, we have ice sheets on both of our poles. And in the yellow bands are times called greenhouses, when there is no ice, or at best ephemeral ice at the poles. And if you look far left of this on this timeline, the blue is indicative that we are currently in an ice house that started 34 million years ago when that CO2 came down to a low enough threshold. So as Lisa mentioned, I'm going to use 3 time periods to illustrate how CO2 and climate have interacted and responded to one another in the past. And these are going to cover a time period 56 million years ago, all the way through to a time period as far back as 300 million years ago. And it'll cover these greenhouse and icehouse states. And ultimately, the message will be the same, that CO2 and climate have always been coupled. But the other message is that even though when you look at these three globes, you can see that the continental configuration was really very different in each of these. Certainly the climate conditions and the ecosystems that lived at the time were very different. But what we've learned from data studies and modeling studies is that the processes that we learn, the climate processes we learn, are transferable under these different climate states and at different time scales, and are thus valid for understanding our future. So we're going to start with the first one, the Paleocene-Eocene thermal maximum, because that is the one that has long been considered the nearest analog to what our near future may bring. So this Paleocene-Eocene thermal maximum was a very abrupt warming that happened about 56 million years ago. And as this inhabitant of Nunavut, Canada, in the Arctic Circle, is holding a poster, and that poster is showing what this region in the Arctic Circle might have looked like 56 million years ago. Now, clearly he's standing on sea ice today, but at the time, the proxies tell us that the Arctic had no ice, that it was primarily fresh water, not even marine, even though it's an ocean. It had so much fresh water on it because the rainfall levels were so high, very hot and very humid, and that there were ecosystems in there that looked like swamps. The culprit behind this abrupt warming was this massive injection of carbon to the atmosphere. And this warming that came with this massive massive injection of carbon led to some very strange things in terms of the things living on Earth. On land, there was dwarfism. And what you're looking at here is a 2-foot-high horse. The primates saw their beginning at this time. The earliest primates here, you see the fossil on the left, these are effectively lemurs, and they are, for those, for presumably everyone online believes in evolution, these are really at the bottom of our evolutionary tree, thanks in fact to this abrupt warming that came on. Now, the warming was about a 5 degrees warming on average, but double that in the polar regions, in particular in the Arctic. Now, how do we know about this injection of carbon and this warming? Well, we know this from proxies, things that we can measure in things that lived in the ocean at the time. So the massive injection of carbon, we know because carbon isotopes that are archived in organisms like this microfossil, this literally microns to millimeter size organisms that lived in the ocean and that were made up of a mineral called calcium carbonate. Has calcium, has carbon, and oxygen. And that, oh, sorry about that again, we're going the wrong way. That carbonate, the carbon in there, allows us to measure the carbon isotopes. And those carbon isotopes tell us that there were these very rapid decreases in the ocean seawater. And that is recording this release of massive amounts of light carbon isotope, CO2, and other greenhouse gases. What you're looking at in this stack of records here, and that is highlighted by the yellow band, are records from deep sea sediments that were taken from cores in the Pacific Ocean. And the yellow band is highlighting the interval that is this abrupt warming. Now we know from the same microfossils, we can go in and look at a different isotope, one called boron. And from that, we can see this major change that tells us there was a 0.3 pH drop or acidity in the surface oceans. And we know there was this warming because oxygen isotopes in the exact same fossils shown here in these lower two blue curves, they show a shift upwards, telling us that there was about a 4 degrees warming in the ocean as well. Now, this time period saw the oceans, both the surface waters and the deep waters, become acidic. And at the upper right photograph is a colleague of mine named Jim Zakos from UC Santa Cruz. And he has spent a couple decades studying this time period. And he's showing a core, a sediment core from the seafloor in the Pacific Ocean. And this very rapid shift from these light colored sediments down here to this knife sharp shift into red-brown sediments is the record of this acidification of the ocean, because the lower white sediment is full of carbonate. And as soon as you cross that line into the red, all of that dissolves in this acidic ocean. The same core shows a much more gradual shift out of that red into, into that white or tan again, showing that the recovery out of this event was much more slow or gradual. Now, the culprit behind, or the smoking gun behind this carbon release, in this case, is most likely methane gas that was released from ice in which it was entombed. And if you look at the little inset crystal, sort of crystal model down here in the lower right, you can see that gas literally entombed in an ice crystal. And these ice crystals make up these hand size. This is a hand size sample of what we call methane hydrate, or basically frozen ice around methane. And this particular sample is actually from one of the basins off the coast of California, about 500 meters depth. And at the time, just like today, we know there were these methane hydrates in sediments all along the slopes around the continents of the world. And presumably, the warming of the ocean waters at these depths led to the melting of these methane hydrates. Now, this diagram speaks to the fact that we now realize the amount of carbon that was released during the PETM, released to the atmosphere, was on par with what we project for the business as usual carbon emissions for what we have already released to the atmosphere and projected in this black peak for the next 250 years. Now, the graph on the lower axis, or the x-axis, is a timeline. It's not linear. And the vertical, or y-axis, is the release rate, so the carbon release per year. So the black being then the current experiment, anthropogenic one, and in red, the release for the PETM. Initially very rapid, although still 5,000 years, and then slowly tapering off for maybe even 20,000 years. So when you look at the rates then of release for the modern experiment, the business as usual, we're talking about a release of about, we say, 10 petagrams per year. And if you're curious what a petagram is, it is 1,000 billion kilograms of carbon. So 10 petagrams of carbon per year, or if you like it in ppm, 3 ppm per year. And you compare that to the PETM over here, and you can see that it is a full order of magnitude faster than our best studied and what we think is perhaps one of the most abrupt natural warmings of the past. Now, with this lower graph speaks to then how does this translate to temperatures? On the vertical axis, temperature change from today versus time on the x-axis. And the red line is the business as usual scenario I just talked about, suggesting a 1 to 4 degree rise over the next 100 years. And the blue line is the temperature changes that happened during the PETM over that 20,000 year period. And I think, the rates there are 0.025 degrees Celsius per 100 years. So I think you can appreciate that we're talking about temperature rises in our near future 100 times greater than what we had during this abrupt global warming event. Now, this particular abrupt warming event, like actually quite a few in the geologic record that we now know well, were superimposed on very different background states than what we live in today. We're in an ice house today, but these were superimposed on greenhouses. And the one I just spoke about was superimposed on this 200 million year greenhouse time. And I just want to briefly say something about what we are learning about that condition. So that what you're looking at here in this diagram is what we call temperature gradients across latitudes. This is temperature on the y-axis, and that's sea surface temperature around the world. And on the x-axis is, is the latitude from the southern pole across to the equator to the northern pole. So latitudinal temperature gradient. In the colored symbols, those are actual data on sea surface temperatures across those latitudes during this greenhouse time. In gray is the modern latitudinal temperature gradient. And I think you can appreciate here that not only were the tropics warmer, but look at the poles, significantly warmer than present day. And the overall latitudinal temperature gradient strongly depressed or dampened relative to today. Now, the reason this is interesting is because this condition raises a real paradox for our understanding of future climates. Because climate models, the same exact climate models that are being used to predict or forecast our future conditions, fail each and every time to be able to reproduce these dampened latitudinal temperature gradients. In particular, they can never come up with these really high temperatures that we see in the northern polar regions unless they crank CO2 up very, very high. And we know that's not reasonable based on our proxy records from the past. So what this tells us then, what this data model mismatches tell us, is that that the climate may be much more sensitive to greenhouse gas forcing than we fully understand at this time. And in fact, the very latest climate model that's come out of the US that is being used right now for the next large-scale study that will come out for our future projections, that climate model is suggesting that temperatures on Earth may actually increase by 5 to 6 degrees for every doubling of CO2. Very high sensitivity. Okay, so let's look at another time of abrupt warming during this greenhouse, because this one allows us to say something about the ecosystem. This particular time, 201 million years ago, was called the Triassic-Jurassic boundary. And it's really well studied because, as the diagram on the lower left shows, and this diagram is of diversity, the y-axis here is the number of animal families and their diversity change through time, their decrease in diversity through time over the last 500 million years. And this particular Triassic-Jurassic boundary, shown by the red arrow, was a time where we saw 50% of life in the ocean go extinct, and about 80 to 95% of vegetation at the species level on land go extinct. And what the arrow is actually pointing at is that this particular event is the third largest extinction of the 5 big ones of the last 500 million years. And it was an interesting extinction because it was a time period that saw the loss of, excuse me, let me decline that, gosh. It was a time period that lost 4 major families of reptiles. And many scientists believe this opened up the world for the evolution of dinosaurs. But what I want to talk about in particular for this example is what the vegetation was doing and how it was responded to climate, but interestingly enough, how it may have also affected climate. So what you're looking at here is a turnover, major change in vegetation for one place, for an area in eastern Greenland 200 million years ago. So artists' rendition of what the vegetation looked like on the top before this big event, this abrupt warming. Nice, dense, very rich forest of gymnosperms. And then across that extinction and warming event, a turnover to a much more swampy-like ecosystem full of ferns, which are very typical of opportunistic plants when things get stressful. And on some fossils, fossil leaves from this time, you can see that you can actually peel these things literally off of the rock. They're so well preserved. Remember, these are 200 million years old. And because we can remove these and they're so well preserved, we can actually use these to calculate what the CO2 was like at that time. So how does this work? When you look at these leaves, they actually are preserved as what we call cuticle. It's the waxy layer in leaves. Very much like the forest floor when you walk on it and you see dead leaves on the floor that may be from the last year's shedding. That's cuticle. And that cuticle, that waxy layer, has on it breathing pores, or what we call stomata. That's where the plant takes in CO2 for food and where it releases its waste product of water and oxygen to our atmosphere. And what we've learned through many different experiments and from studying live plants is that the amount of these stomata on a given area of the leaf actually decreases when CO2 is high. And that's because they probably don't need as many because there's lots of food in the atmosphere, lots of CO2. And vice versa, when CO2 goes down, even the next leaf on a given plant, when CO2 goes down, they have more of the breathing pores to take in more of the CO2 food. So this inverse relationship is largely in part behind the construction of CO2 records from fossil plants. And what you're going to see here coming up is a microscope image of a 201 million year old leaf, the cuticle. And the nice flower looking white areas, that's the actual breathing pore and its protective cells around it. And then it's swimming in a sea of these brown cells, which are the epidermal cells, equivalent to your skin cells. Remember, this is a 201 million year old leaf. So these trends, and I try not to show you too many of these because I realize they can get pretty technical and boring quickly, but I want you to think of these, this green and black lines as time trends. So oldest down here, youngest at top, across this abrupt warming where the arrow is, or this Triassic-Jurassic boundary. And what these green and black line are is they're two different genera of plants. It's an index of how their stomata were changing across this time period. And so what the measurement you're seeing here is basically how much change on their leaves through time. And it's saying that about 50 to 60% decrease in the amount of stomata across that interval. And you can use that to then calculate what actual CO2 was doing. And that's this red trend on the right. So CO2 doubled across that abrupt warming and extinction. It went from about 800,000 parts per million before the event and doubling to about 2,000 before it returned to background levels. But what just popped up is that the rate of change is minimally an order of magnitude, if not 2 orders of magnitude slower than present day, despite the fact that it was a major extinction and had major impact on the terrestrial ecosystems. So the same leaves, not only do they have fewer stomata, but stomata got smaller when across this warming event. And what you're looking at in the trends here is that we can take this information and apply it to mathematical models and see what that impact of fewer stomata and smaller stomata would do to their ability to move water or transpire water to the atmosphere. So what these trend lines are now saying is that the amount of transpiration of water to the atmosphere, the amount of transpiration of water to the atmosphere was halved across this global warming event, whether it's at the leaf scale or the canopy scale. And this would have had enormous implications for the amount of water vapor that was in the atmosphere in the area or regions associated with these forests. So what this tells us then is that these plants were able to physiologically force the water cycle and climate. And this flowchart will explain or summarize what this really means. We start out with lots of stomata and they're big. We have a CO2 rise, that doubling that the data tells us we have at this event. We get half the stomata, they are half the size, which reduces the transpiration of water vapor to the atmosphere. The water that would have gone to the atmosphere that's in the plants has to go somewhere. And what it means is it goes out the roots and it gets in the soils. And when the soils become saturated, it becomes surface runoff. And surface runoff erodes soils and strips nutrients from the soils. Now that surface runoff eventually goes to the groundwater or to creeks and streams, and eventually goes to coastal waterways. And if you have all these nutrients that are being supplied to the coastal waterways, you get what we call eutrophication, or a decrease in oxygen of the waters. That's happening along coastal waterways around the world today. When you have that eutrophication, that lack of enough oxygen and high toxicity in the waters, you have to impact the marine biodiversity. So what this study tells us, and many others that we've looked at through time, is that the connectivity of the Earth system, you cannot change one part or one component of the Earth system, like change of CO2 to the atmosphere, without impacting all components of the Earth system, from land and atmosphere to the oceans. So as I said, we call this physiological forcing of plants. And what I've just described is that the plants responded to climate and in turn impacted the climate once again. And this physiological forcing of plants, we now appreciate, is probably pretty typical under conditions of elevated CO2. But what's important is that there are no climate models to date in any country that is able to actually consider this physiological forcing as part of their modeling. And that means that we're probably underestimating some of our projections. So the last example, I'm actually sort of ironically going to go to the last ice house. I've been talking about greenhouses, but now I'm going to go to the last time we had ice at our poles. Remember, we're in an ice house today. So now we're going to go back 300 million years. And this ice house is commonly considered maybe the most acute, certainly the longest lived and the most widespread ice house of our last 500 million years. Ice, though, was pretty much distributed in the southern hemisphere, polar regions, and even mid-latitude. This is an important time to study as well because it is our only record where we have multicellular life on Earth, that we go from an ice house like today to a time of no ice or a greenhouse within about 2 to 10 million years of time. This was also an interesting time period because this was the evolution of the first wooded forests or plants that made up the forests. And you can see a diorama from the Smithsonian for one of these typical tropical forests. They were actually forests that were dominantly wetland forests, and these biomes, they're shown here on this map, their distribution in blue and green. They were really widespread. And they were made up of a lot of different plants, but one of the dominant ones was this enigmatic lycopsid that you see here on the lower right. These things were like telephone poles. They had no vegetation up till they got to about 60, 100 meters tall. And then they had a little cap of baby vegetation. And they coexisted with another dominant plant that we call medulloceans. These are a group of plants. And it might look like a fern to you. These are these guys here. And in fact, they're not ferns. They are Earth's first seed plants. And together, the lycopsids and these medulloceans made up much of this forest that was swampy, and they became peats. And those peats are the coals that today, and the last that we've been mining from North America and China. We also know that this time period was a very dynamic in its glaciation history. The ice came and went very much like the last couple million years on Earth. So here you're looking at a southern hemisphere perspective of the continents 300 million years ago. And in white and blue shades are where the ice was distributed. And you can see there are many different ice centers, or where the ice would have emanated from and waxed and waned from. As I mentioned, the ice at times coalesced, it was so large, and at other times would withdraw into these ice centers. And with this were very large sea level changes. And our work suggests that this dynamic glaciation history was driven by CO2 changes. And CO2 changes over the range projected for our future. Now, just like with the last example I showed you, we can use plants. So here's a 300 million year old fossil leaf. You can see the exceptional preservation. The yellow is the area, oh goodness. The yellow is the area of the stomata. In fact, the stomata is this little area here that these guard cells around it have closed the stomata. And all around here are these epidermal cells. And the dark spots are actually the bases of where hairs came out of this leaf. Lots of leaves actually are hairy. Probably help them deal with rainfall, exceptional high levels of rainfall. So we can use these leaves, just like we did in that 200 million year scenario, to reconstruct CO2. But we also can use minerals that formed in ancient soils. And this is a soil, a 315 million year old soil in a mountain face in northwestern Argentina. And from that soil, we can collect minerals like this one on the lower left. This is actually a mineral carbonate that formed a cast literally around the roots of the plant living in the soil. And we can go into these minerals and we can go after their carbon isotopes, as well as the organic matter entombed inside of them, apply those to a mathematical model, and actually come up with CO2 estimates for past atmosphere. So I'll show you one of these. This is a CO2 estimate, the yellow and black line. We're going to follow the black line for 16 million years of time from oldest to youngest. The uncertainties are shown by the dashed line. What you can see is that CO2 over the 16 million year period pretty much ranged between 200 and 600 parts per million. And it fluctuated on the hundreds of thousands of years, very much similar to our last million years of time on Earth. And interesting enough, this variability, though, was once again orders of magnitude slower than we are seeing with the rise in the last 100 years. Now, we know that these changes in CO2 led to lots of climate change. We have that in all kinds of evidence in the geologic record. But here I show you some results that we get from climate models. So one of the things we do is to use the exact same climate models that are being used for the future projections. We use them to look at this past, to look at how CO2, and in this case, how ice responded to the CO2 levels. So these globes are showing you for different levels of CO2. The top is 280 parts per million, then 420, 560, and 840 parts per million. It shows you the sensitivity of the ice. That's these kind of gray, purplish colors. The sensitivity of the ice to these levels of CO2. And what it says is that big ice sheets could only be sustained under 300 parts per million. And at about 800 parts per million, ice was almost gone from everywhere in the southern hemisphere. But between 300 and 800 parts per million, ice was distributed on Earth, the models suggest, very similarly to what we see from the actual evidence in the field or the geologic records from these same basins, suggesting that our modeling is pretty successful. But it also says that ice was very sensitive to these changes in CO2. And in fact, we see large sea level changes in the rock record related to these changes in ice volume. So I want to go back now to where I started in this talk, which is that lessons from the deep past have relevance in that they provide a unique component to the discussions of climate change, and specifically that they are our only repository of how CO2 will respond in the future. And here in the top, you see the release of fossil fuels since the 1900s in black, and projections for the future to 2100. Business as usual, the red curve. And what this suggests is that, well, first of all, on the business as usual track, we are already at this globe down here, the Pliocene, what we saw 3 million years ago. And if we continue on that trend, we could be the beginning of the next century in conditions we haven't seen even as far back as 90 million years. And even this intermediate trajectory where we get to peak emissions by mid-century, we could be looking at conditions that we haven't seen for 50 million years. In this graph, I'm comparing the total magnitude of CO2 release during these time events I just presented, plus some others. So total magnitude on the y-axis of CO2 emissions for the entire event versus the rates of release of that CO2 on a logarithmic scale on the x-axis. The red stars, that's where we are today at 30 billion tons of CO2 release and projected to the next 200 years. And I think you can appreciate that the total magnitude of change for our next 200 years is on par with that of the past events I talked about. But clearly, there is no overlap in the rates. This was far faster, now our future, far faster rates, current and future, than any time in our past. Meaning that the magnitude of CO2 emissions today are of geologic magnitude, but are happening at a geologic instant, at rates that are unprecedented in the rock record. And I just want to say briefly, how fast could we recover from this experiment of anthropogenic CO2 emissions? So here you've got a timeline on again on the x-axis, CO2 on the y-axis. In black is the CO2 trend for the last 300-some thousand years. And the colored lines are those projections for CO2 of the 3 CO2 emission scenarios that I talked about, projected out over tens of thousands to even 300,000 years. They show the rapid rise we've been talking about, and they show the very slow decrease in CO2, regardless of which scenario, by natural processes in the atmosphere that can sweep out the CO2, literally absorb it out of the atmosphere and sequester it. But these natural processes are far slower than the human time scale. Tens of thousands of years and perhaps hundreds of thousands of years to get back to our pre-industrial levels. But I don't want to leave you on this dire message. We have enough dire messages these days. So I'd like to just quickly throw 3 more slides where I want to mention that there are fixes that are important. We all know that humans have been behind much change on Earth. They have, in the last 10,000 years, spread around the globe. They have perhaps at this point, we know they're the biggest agent of change. And as far as actually even changing the atmosphere, as we've talked about. But that potential for change also includes the potential for great innovation in technology. And what you're looking at here, this odd contraption that the Swiss designed, is a machine that can actually sweep out or suck out CO2 from the atmosphere. It takes it out, it changes it or compresses it into liquid CO2. That liquid CO2 is then injected deep into the subsurface, about 900 meters, where it literally interacts with rocks, like this piece of lava here. And the red part is the lava. It interacts with that rock, and then it puts down new minerals, this white mineral, calcium carbonate. The CO2 is literally sequestered permanently from gas into rock. And this can be scaled up. The technology is there already to scale this up to where we could remove enormous amounts of CO2 by this technology. Not an ideal fix, but certainly one that is available. And this can even be scaled up to grandiose levels. You see here this football-sized paddle in Central Park in this computer rendition. This paddle is called a Lackner unit. And just one of these is capable of removing the annual CO2 emissions of about 3,000 households. And lastly, this is a time of great opportunity in the sense of alternative energies. And I just wanted to comment that the alternative energies like wind and utility shown in yellow, and wind and solar shown in yellow and green here. This is a graph that shows the dollar per megawatt hour of these alternative energies relative to our fossil fuel energies and nuclear. And what it shows is that in the last decade, the cost of going green has dropped tremendously. So much so that we are now at the point where electricity from solar and wind is the cheapest source of electricity for 66% of the world. And in the next 10 years or so, it's estimated that renewables will be cheaper in terms of electricity than electricity made from burning fossil fuels almost anywhere in the world. So I think we can say that we have the opportunities coming with the innovation of humans to really slow the curve, the growth rate of climate change. So I want to thank you again for the opportunity to share this with you. I'm sorry that we weren't able to do this in person, but I hope that I was also able to perhaps give you a distraction from what I think has been weighing heavy on the minds of all of us in these last few weeks. And with that, I'd love to take some questions. Okay, I see that we have one from Stephen Slaughter. Will we see a short-term effect in the atmosphere from this current quarantine period? And could that be used to correspond to potential projections for restraining emissions? We won't see it in the atmosphere, and it's a really good question. We will not probably see it because CO2 is really well mixed in the atmosphere within a year per hemisphere, like in the northern hemisphere, and then between hemispheres within a few years. And so what we do see is we will see like the effect of photosynthesis by seasons, the growth, the periods of high photosynthesis, the summer and early fall, and then we see the drop off of photosynthesis. We see that in the record, but I don't think we will see it in the CO2. It'll be interesting if we do, because that will be a reason to take pause and think about that, what the experiment might tell us. Okay, a question from Mark Evelsazor. Sorry if I didn't get that right. You discussed the earlier greenhouse times when the poles were swampy, and this was generated by a massive increase in CO2. What triggered that massive CO2 increase? So that's interesting. That one was a very widespread event of release of lavas, basically, volcanism. And it wasn't that there was a lot of volcanism to the atmosphere, but there were these huge release of lavas over the land. And that, as it was going up onto land, it actually baked lots and lots of coals. And those coals released lots and lots of CO2 to the atmosphere. And the models tell us that it was certainly enough to do that. Paula asks, you say that plants are able to force the transpiration rate. So should we be planting a lot more plants to help moderate our conditions? It's really interesting. There's an experiment that was done down in the Everglades, and they did it for 20 years now. And what they could show was that over a 20-year period at least, literally as CO2 has been going up, the next generation of leaves on a single plant, not even a new plant, but a single plant, the next generation of leaves would change their stomata and thus change the amount of transpiration. And this has been sustained for 20 years. Now, the question that a lot of botanists and paleobotanists and ecosystem modelers are asking is there a point where this will no longer change? You know, where the plant sort of just says, I'm saturated, I can't make any more changes. Even the next generations of plants. And we don't know the answer to that, but for certain, we should be planting more plants. And in particular, in the more temperate and boreal forests where they make the most difference in terms of also taking up more CO2 and sequestering that CO2 in the dead, buried organic matter. And then, is this why I hear the poison ivy is getting more toxic? Exactly. This is really interesting. What's happening is that whenever we see these warmings in the past, like the one that I talked about where the plants went to swampy, opportunistic plants, the ferns, well, this is what happens with every warming we've studied in the past. It's the opportunists in terms of plants who take over. They do really well under stress, whereas the others that are more tuned, finely tuned to the conditions that they evolved in, they don't do so well. So the opportunistic plants like poison ivy and mustard seed and poison oak do very well. And then on top of that, they put out that much more pollen and they become more highly toxic to their hosts or to those that interact with them. Meredith asks, how useful are these events for proxies of future change when the inherited state is different for past events? Okay, that's a really good question too. What we know now is absolutely, and I think this is what you're asking, that the state at which we start very much influences the sensitivity of the climate system to CO2 changes. So the reason I talked about that time period 300 million years ago is because that is the last time we had ice on Earth. That isn't the recent. And under those conditions, we actually do see a doubling of the sensitivity of the climate to CO2 doubling. So yes, it does matter. Skelly asks, and I bet it's something, Kelly, I just want to thank you. Oh, thank you. I feel like I have a very clear understanding and perspective of where we are and need to go. Well, thank you. That's always one of the nicest things to hear is if people feel that they've gotten something to take home with them. Lou asks, I read that during the 9/11 reduction of air flights, the amount of water vapor from the flights reduced so much that it created a measurable reduction in global temperatures. Is that true? Well, I actually don't know. I can't answer that. I'm not sure I would think that could be true, but I'll tell you why. Contrails do not make immeasurably enough of a difference compared to all the other things that change water vapor, including plants in their times of seasonal growth when they have lots of leaves versus when they don't. I don't know specifically for 9/11. I'd be very interested if you know where you have read that. I would love for you to pass that on. I think my email, it might still be on the screen. Yeah, it's interesting. For those of you still on, thank you for being patient with my very sensitive mouse. It's the first time I've seen it so sensitive. I'm not sure why. When we ran our trial on Monday, it worked fine, but thank you for being patient. So Mark asks again, the CO2 removing devices, do they require fuel to operate? Yes. And how is the CO2 put in the ground? So absolutely, you hit the nail on the head. They are still fossil fuel powered, and that is a huge issue. Kind of like desalination plants for getting fresh water from seawater. And the benefit is still higher than the cost, but it isn't always a good solution, because it says we can keep burning fossil fuels and just consider taking it out. It'd be better just to put less in to the atmosphere. The CO2 is injected down into the ground, and the ones I showed you, it's just powered by a pump. It goes about 900 meters down. There are much bigger systems that are being still tested in the US, are used already for a while in Canada, and that's where they can inject the CO2 from the coal burning plant or from the oil refinery. They capture the CO2 right out of the plant, the refinery itself, before it even hits the atmosphere. They sequester it, they then under compression make it into liquid CO2, and then with power are able to pump it back down into the very reservoir deep in the ground where they removed the oil or coal originally. Tom asks, or Lisa from Tom says, the CO2 extractor at Peace Be very expensive, is it? Well, these technologies probably are, but the cost is certainly an issue. I think the cost in terms of fossil fuel burning is now considered as big an issue. We would love to see these things in the future be more efficient, but they are not. You're absolutely right. They are not yet out there everywhere because of cost, the fossil fuel requirements, and then the eyesore, the not in my backyard issue. Where do you put these? Would you put thousands of them in Antarctica? That's the sort of question people are asking, or in deserts. David Houston asks, okay, did you buy the home in the Sierras because you see it as oceanfront property someday? Funny. No, I did because we are real outdoor enthusiasts. Okay, this is bad. I'm just going to come out clean. I thought we should use some of the gains in the stock market, and I think these days I'm quite happy we did. And the valley can get very, very hot. But I will tell you that I share with students a map that I've made of 6 feet of sea level rise, which is high. That's the highest estimates for this century. I share a map with students that show that rise, and it puts Davis, California, down in the valley at about 54 feet of elevation. It puts it literally on the storm surge front. So kind of murky wetland kind of environment. From Charles, it seems that there were spikes in biodiversity immediately preceding some of the extinctions. Do we know why? I don't know that is a consistent thing. And I really can't speak to that. That's my weakest suit. I'm not a paleontologist. I work certainly with quite a few. I'm not sure that there were spikes in the examples that I showed you. Now, in the past, what could be happening is, if you know of that from other time periods, is that there certainly are families. It's usually at the genus level that are opportunists, and that might be what we're looking at. But I can't say much more than that. Mark says you described a self-reinforcing feedback loop with coal earlier in presentation. Are there feedback loops possible to put us on a good path to reducing CO2? There are many, actually. There are many, and I'll say that there are short-term ones. The ocean is a very good sequester of CO2, and it can hold it down in the deep ocean for thousands of years, because CO2, if you can get it down there, usually it's liquid CO2, it is actually more dense than seawater down at the very depths where it's very cold, like 3-5 degrees. It eventually will come back up with the circulation of the ocean. But of course, the CO2 sequestration in plants and the burying of organic matter in soils and in dead plant material. But those are short term. The real fixes are going to be this long term sweeping through minerals, the formation of minerals that I was describing in that extractor. And basically what's happening every day, but it's just so slow, but what's happening every day on the surface, every soil, every exposed rock is interacting with CO2 in the atmosphere that gets dissolved in rainwater or gets dissolved in soil water. And that becomes an acid, a carbonic acid. And that acid is always eating away at the rock and the soil, I mean, all the time. And that process, just like those extractors I talked about, is taking the CO2, dissolving the rock, and is then getting taken away by runoff and groundwater to the oceans, where shells are made, where organisms that need skeletons will make those out of that dissolved material. And now, once again, you've sequestered the CO2 from the atmosphere into the ocean. That, though, is happening on tens of thousands of years. And that's what's going to ultimately bring CO2 back down, no matter how high we may bring it with fossil fuel burning. It's just that it takes tens of thousands of years.
Is there
and
another
I see
question?
somebody asked, thank me for letting them see our cat. And I have to say, I am extremely thankful that this cat wasn't crying the whole time, because he can be very talkative.
They were very observant. That was that's actually a topic of discussion right before we went live. Like what's the cat going to do? So thank you, Professor Montañez. What a wonderful talk. And thank you everyone for participating in tonight's webinar.